Hey everyone, this is Physics 2211, Lab 5, Slinky Fall. The purpose of this experiment was to predict the motion of the bottom of the slinky when it's being dropped and compare those results between the computer model and the observed model. And the results of this lab is that the computer model and the observed model had similar results, and the bottom of the slinky remained motionless until the top of the slinky falls to the bottom. And some key concepts that we used in this lab was the velocity update formula and the potential update formula from Newton's second law. And the assumptions we had is that net force is equal to force of gravity plus force of tension plus force of drag once the top of the slinky reaches the bottom, where there's the force of gravity, force of tension, force of drag um, in their own equations. And here are the tracker model. As you can see, as it falls down, the bottom of the slinky actually does not move until the top reaches the bottom right about now, and it begins to fall. And the system, in this case, obviously, is the slinky, and the surroundings, everything else. Now, the code that we use, where the ball or the slinky has a mass about 0.25 kilograms, and this is initial position from tracker. Velocity starts at 0 as it's at rest, and we have the force of gravity as well as the j hat, and b, which is the drag coefficient, which we got by guess and check. And here the loop where we use the position and velocity update formula. But while time is less than 8 seconds, the total force is only weight force and force of tension of the slinky. But when time is greater than 8, the force in this case would be net force plus weight force plus the force of drag, and tension is no longer there since the slinky already meets. And here's the code running. And to compare the results between the two graphs, this is the tracker model of the y position as time increases, and this is the computer model. And the graph on the bottom compares those two, and you can see the data had very little deviation. And possible sources of error to those deviation is that the coefficient of drag was obtained by guess and check, so that could affect our results. And the center of mass of the slinky was estimated in tracker, so human error could possibly exist. And to finish it off, discussion and conclusion. To answer the question of does the bottom of your model slinky stay stationary just like the video? And the answer is yes, the bottom of the slinky will stay stationary as the tension force cancels out the gravitational force as the slinky shrinks, thus making the bottom of the slinky motionless until tension force stops. And that's when the top meets the bottom. And that's when only the total force is drag and weight force.